Good morning, everyone. Thank you so much for joining us today in this new OSI webinar. Today's topic is going to be improving gas separation in rod pumps, gas separator designs, and selection criteria. My name is Carlos Portela. I've been with OSI a year and a half in the technical service department. We have today my colleague Neil. Good
Good
morning,
morning,
Neil. How are you doing?
Carlos. Thank you all for joining us today in this webinar. We're excited to show you some of the designs and selection criteria. And hopefully by the end of this presentation, you all will have some questions, obviously, and get a much clearer picture of what exactly we're trying to do when it comes to gas separation, especially in rod pumps, especially in this downturn, when we're trying to improve the separation efficiency and increase the runtime of all of these rod pump systems. My name is Neil Johnson Vaz Happily. I've been with the company over 2 years now, working in the technical department, working on improving the separator designs, recommending the right gas separators for rod pump CSPs. But thank you all again for joining us today.
Thank you so much, Neil. All right, so we're gonna show you the order of the presentation. So we're gonna be explaining to you. So we're gonna start with a little bit about an introduction on the gas failures and how the gas affect the rod pumps. We were gonna be explaining the gas separator, what the downhole gas separators, the ones that we have in the market today. Then we're gonna go through a selection criteria, then compare the efficiency of the separation between each gas separator, and then we're gonna explain some operational guidelines. All right, so basically, for the ones that are not familiar with downhole gas separators, all right, so in this case, we'll be installing this below the pump. In this case, the gas is going to be affecting the efficiency of the pump, so it's super important that we identify how severe is the problem and if we have a gas problem or is just like a fluid level or like kind of an inflow problem from the reservoir. So that's why that's what we meant with target identification, is that we need to evaluate how severe is the problem and then what the limitation do we have in the wellbore, and then proceed to design our gas separator, starting with that information. So we analyze all the data, starting with production information and pressure decline on each well, so we can identify the amount of gas that we are going to have in each case, and then design the gas separator. Always we've been very on top of the advice that we have on the installation procedures, and that also we need to we have some parameters that we always recommend to increase the natural gas separation efficiency. And of course, we always try to monitor the well and how it's behaving, how the production is enhancing, and also like the separation efficiency of the gas separator. So in order to understand what we're dealing with, so basically we have gas problems either in conventional and like unconventional reservoirs or unconventional wells. So here in the Permian Basin, we have many horizontal wells where you will see that flow, slug flow, is pretty common. So it's how the horizontal well will flow. So what we need to from the horizontal well, from the horizontal zone to the vertical zone is on the toe. Basically, it's gonna create kind of like a turbulence there. So we're gonna be creating like small bubbles, big gas bubbles, and so we need to identify these kind of situations to see how to approach the issue, right? Because like the bigger the bubbles of gas they are, so it will be easier to separate them, and when they are small, so it will be hard to separate these gas bubbles. So yeah, after like many years, the company has been developing many solutions for every single kind of situation, and we're gonna be explaining that to you later on. here we just wanted to show you. We showed this video on the previous webinar for ESP gas separation, right? So basically, what we want to show you here is how the horizontal zone works. So basically, by gravity, we have two phases here. The gas on top of the wellbore, and then at the bottom will be the liquid, and then the gas, because it has a higher mobility, so we'll be pushing that fluid into the toe of the well. So now let's go forward a little bit. So here in the toe, so we will see that some of the liquid is flowing back. Um, because of that gas bubble, so that will create turbulence here. So that's what I was I mentioned before. All right, so we'll have the different size of gas bubbles here, and also we can have the entire slug flowing into the pump. So first of all, we will need to break that gas slug, and then we will have to separate as much gas as possible to avoid that gas entering into the pump. Why? Because this gas inside of a rod pump, what it causes is it causes many failures and production and decrease in an important decrease in the pump efficiency. So basically, what we want to show you here is that just put it right here. So basically, we have a typical pumping problems here, which is like the fluid pound, the gas locking. So basically, what we want to show you here is that for the ones that are not familiar with this topic, so when we have fluid inside of the barrel in the upstroke, what is going to happen is that that gas is going to expand, and then on the downstroke, right, the plunger is gonna start compressing that gas, but the barrel is not gonna be entire filled by liquid. So at some point, the plunger is gonna hit the fluid level inside of the barrel, and it's gonna buckle in. It's gonna buckle my rods. So that what is that? What happened with this? So basically, the rods will cause wear on the tubing, and then we can have broken rods. And then we will have to pull. So there's many disadvantages of working with these conditions. So we're gonna explain you now, because like the difference and how we identify these problems. So basically, many companies, and so over the years they call gas interference and fluid pound and gas pound. Sometimes they call fluid and gas pound like the same problem. But so we want to just show you really quick. So how do we evaluate this? So let me just put the pen right here. Where is it? There you go. All right. So basically here, so we have um, a good pump village, right? So in the upstroke and the downstroke, the the uh, the um, the traveling valve is opening when it's supposed to be open, so we're not having any problems in the transferring the load of the rods. So now here we start with the gas interference. So now we do have it's due because the well has a lot of gas, or we're pumping too fast. So we got some gas inside of the barrel. All right. So what is happening right now is that this section right here, all right. So this section, what it means is that the gas is compressing here. So basically, the traveling valve is not opening where it's supposed to be open. So what we're losing is pump village here. All right. Now the gas interference. So basically, we see this when we have high GLR and GOR. When we talk about fluid pound, it's more like the capacity of displacement of the pump is higher than like the quantity of fluid that the reservoir can give up. So basically, we're producing more than the inflow of the reservoir. So basically, we're gonna be pumping off the well. So at some point, the fluid level inside the barrel is gonna be insufficient, and the plunger is just gonna hit that fluid level, buckling, and even like you can feel that at surface. So that could cause many problems. And then the gas pound is that we can identify and differentiate these two based on a second, based on the liquid level. So basically, there you go. So on the liquid level, so we can identify when the liquid level is stabilized. So we can see if we are producing below the bubble point, and if the pump is ingesting a lot of free gas, and we still have an important fluid level, so but we can say that we are seeing the gas pound issue right here. So we can approach that problem, increasing the pressure of the casing when we have enough fluid level, so we can keep that gas in back in solution. So as we mentioned before, there is many disadvantages of having gas in the rod pumps, including rod buckling, fluid pound, gas interference, gas locking, many tubing and rod failures that you're gonna have you pulling your well, having delay production, and so on and so on. So um, here we have two, just right quick to explain you like two fluid level tests. So basically what we have here is check. Okay, there you go. So we have here fluid level, right? But so we need to understand this in the annular area, right? We will have a differentiate fluids based on density. So at the very top we will have gas, then we have a gas liquid interface, and then we have a liquid level. So here you see here when you see fluid properties, sorry, you will see that there is a percentage of this level above the pump. So when you say when it says here liquid level above the pump 73.21%, it will refer that this level right here, all right, is gonna be represented from the pump to this level. So let's suppose this. So 73.21%, this is gonna be related to liquid. And the rest is gonna be gas and the gas and liquid interface. So this is like really important to always identify first before designing a gas separator. And also here we can see like the same effect of the gas interference. So it's affecting our pump village, which should be something like this. So this is what we're aiming. So what we need to do is eliminate that gas flowing inside of the pump. Okay, let's move on. All right, so we have here our type of gas separators. So basically, we're gonna explain this. I mean, these gas separators, they have been used for many years, and the industries, and OSI is one of those companies that they are being developing improvements and enhancements in every single gas separator. So we are always trying to get more data, more information of what's going on in the market, or what are the new problems, or what are the new solutions that we can find to gas separate to improve the gas separation. Right. So here we have the natural gas. So basically, we need to understand here that we have two velocities interacting here. So one will be the velocity, of course, of the liquid, so which is the surface liquid velocity, and the other one will be the slip velocity of the gas bubble. So to have gas separation, the slip velocity of the gas bubble will need to be higher than the liquid velocity. And here when we have the perforations above the pump intake, right? So the gas will be, one second. The gas will be traveling some of the gas, right? So depending on what is your pump speed. So like the gas is gonna start flowing upwards, okay? So let's say, so that's why when we have gas problems, we recommend long strokes and low speeds. So we don't have like high fluid velocity, because if we have high fluid velocity, we will just, the liquid will start dragging all those gas bubbles directly into the pump intake. All right. So yeah, that's why we always recommend that when the problem of gas is severe. So that's our natural gas separator. Now we have our modified natural gas separator. So in this case, we're installing the pump right in front of the perforations. So what we do is that we install an extension, in this case, the deep tube, all right, with the intake at the very bottom to simulate the same concept as the natural gas separator. All right. So basically, it's the same concept. The gas bubbles, due to density, they will always try to flow up. All right. So that's the principle of the modified natural gas separator. And then we have here our poor boy gas separator. So now the poor boy gas separator was developed because we would need to, in this case, install the pump above the perforation. Okay, so basically what we're doing is like to forcing that liquid to travel through a inner we're creating with our gas separator. All right, so basically, I mean, every unconventional well will be this case. So many companies, what they do is they install the pump in the vertical section, and as you know, all the perforations are in the horizontal, in the multiple stages fracturing. So this will be the case for unconventionals. So basically what we do here is that the fluid is going to come here, it's going to enter into the gas separator, and then we're forcing the fluid to flow downwards because the intake will be here. So in this process here, we will be separating gas um, with the same principle of velocity. All right. Let me just delete this. All right, so let's move on. Okay. So we have our modified pour bore gas separator. For this one, what we're doing is modifying the diameter of the gas separator. So now what we're doing here is that we're enhancing our gas separation here in the annular and inside of the gas separator. All right. So what we have here is, because we have a bigger IUD, we will have higher reduction in velocity inside. So it will be easier for the free gas to flow upwards and then be purged by any outlet point that the gas separator may have. And here on the right side, we see a gas separator that is also very popular, which is the Packer type gas separator. So for this one, we will need a packer. So we need to isolate the perforations. So the industry will be using a mechanical packer, rotational packer, and some cases with cup packers. So basically, what we're doing here is like using that casing, that annular space, that cross-sectional area to separate as much gas as possible. So basically, the casing it will be the biggest. The idea of the casing will be the biggest space that you can use. So basically, what we do is that we isolate here with a packer, okay, and then we create a flow path here. So we will have our intake of the system here. Then we will have an outlet point here. So some of the gas is gonna be released from right here, right? Some of the gas it will start rising up, and then at the moment that the fluid starts flowing down, all right. So we will have gas bubbles here, just start rising up and increasing that separation efficiency using that ID case. All right. All right. So let's move on. That will be our gas separation, like the main idea of each one of them. So, what principles are gonna be using in every single gas separation system known today? 1 second, let me just delete this. Okay, so we'll be using the gravity, basically the difference in densities will help us to separate gas. And we say reverse flow. What we mean is that we're creating a flow path or an inner flow path, an inner flow path that help us to separate that gas. All right. So pressure changes in fluid velocity and gas and liquid velocity, and then we have agitation. Okay. So the coalescence of the gas bubbles and baffling of gas. So the bigger the gas bubble is, the much easier will be to separate. All right. So the buoyant force is gonna be higher when you have a big like a bigger bubble. So at some point where we want is big bubbles. Of course, this is way before these bubbles reach the intake. All right. So we have here two of our outside gas separators. So we have on the left hand side our modified motor hovered with a slotted intake. So we have many sizes based on the limitations that we have on the casing, and if we have another problems that maybe we have to consider when we are going for a bigger OD section. As you see here, the neck and the body, they have different ODs, because what we're looking for is a reduction in velocity in this section. We're gonna explain that principle later on with the video, which will be easier. Okay, so here on the right hand side, what we have is the same geometry, right? But on the neck, we will have a screen section. So in this case, what this screen section is going to help us out is to the coalescence of the gas bubbles to create, as mentioned before, bigger bubbles. So these will be like easier to separate later on in the process. And here we have our a combination tool, OSI combination tool, which is a modified motor hover style gas separator with a screen intake, and we enhance the separation with a desander installed below the gas separation bodies. All right, so I'm gonna show you a video really quick. So I just wanted you to know and to understand that we were gonna be using these principles, the Bernoulli principle, energy conservation, a Venturi effect, Coulom's effect, and then gravitational forces. Now, this dual flow connection is going to be incorporated in every single tool that OSI has. So as you see here, our tubing screen, here. So the tubing screen, which is this, our intake section right here, is going to have the dual flow connection right here. Okay. And then our gas body is going to have that same connection here and here. So what we want to do here is that we want to make those big bubbles be kind of filtrated here. So I will show you the video, but as you see, these are going to be the slots. The slots where the fluid is going to flow downwards. And here, I just wanted to just show you at the beginning, here there will be our intake. All right, so for the ones that are familiar with descenders, so we'll have a deep tube, so an inner section inside of all the equipment, and then the fluid is gonna flow through here. All right, so let's go through the video to just show you better. Okay. All right, so now because we have a descender, okay, so our vortex, what is going to happen is going to enhance the gas separation. It's going to avoid any big gas bubbles to reach the intake. So it's going to break those gas bubbles, and if these bubbles reach the intake, all right, they're going to be smaller. And we have a smaller, when you have the smaller gas bubbles that are already gonna flow into the system, it's preferred to be small, and then you can pressurize that to make it easier to manage for the pump. All right, so That's why, and then we have, because we have a desander, we will need to have more joints installed below, right? And it's very important because I mean, mostly here in the Permian, mostly in the Midland Basin, right? So there are many wells that have like a lot of sand, regardless if they're being producing for a year, 2 years, they have that sand either from the frac or the formation. But we will have that, and just to avoid any issues, we will recommend always to install three more joints below the vortex. All right, so this is the vortex as you see here. This is going to be our intake, and then it comes our dual flow connection. Let me just delete this real quick. Okay, there you go. Then this is going to be our gas body. As you see, there's a difference in the diameter. So inside, of course, the ID will be bigger. All right. And then inside we have our deep tube, which is going to connect the intake to the intake of the pump. To the pump, sorry. All right. So let's go through this. So the tubing screen will be the intake of the system. So now we have different slot sizes depending on what problems do we have on the well. If we don't have as much sand, or if we're not aiming to sand, we can get these slots bigger. So we kind of helping more to the coalescence effect for the gas bubbles, or we can just go smaller and start filtrating that sand. Okay, so we have here our deep tube head, which just basically avoid these slots to be for the fluid to flow through these slots. So now let's see if I can show you. There you go. So there's going to be only one flow path directly from the deep tube to the to the um, to the deep tube head, and then to the pump. This is what I wanted to show you. So it's going to be only one flow path, and this is going to be the intake, which is the end of the deep tube. All right. So let's keep moving. So this is going to be our first stage, the tuning screen, which can help us out also to filtrate sand. Then the fluid is gonna start traveling down, and then it will reach our body, our gas body. So in the gas body, we'll have two sections. In the outside, so what we have here is a reduction of area here. So what is happening here is we have a higher velocity, so we'll be applying more energy to those gas bubbles, so for them to keep rising. All right, and then what we have here is also a lower pressure. Okay, so a lower pressure zone, so we can just separate gas here, and then so we have more free gas at the bottom, at the top. So, and then we have when the fluid is already inside, is the opposite. All right, so we're gonna this section, right? What is gonna help us is to reduce the velocity, right? So the gas bubbles will decrease the velocity here, and they will start rising again, and then like here. There you go. See how the gas bubbles there start rising up, and then we'll be purging those gas bubbles through the tubing screen or the intake section. Here we have our vortex, which I mentioned before. It's going to help us to break the gas locks and separate sand. All right, so basically what we wanted to show you here is that pressure drop basically means gas liberation. So velocity is going to be very important in this process with the gas bodies, with the bigger gas bodies. And we also, through years and many studies, textbooks, and field experience, we know that a velocity of 0.5 foot per second is what we're aiming for. So we want to achieve that by reducing that velocity through either one or three gas bodies, and so we will have that certainty that we are separating that gas and reducing that velocity onto that point. All right. The vortex will generate agitation, will break the gas locks, and it will help us out to just be sure that we are pumping clean fluid. All right. My colleague Neil is gonna start explaining you guys how the Parker type gas separator works. All right, Neil, all yours.
Carlos. So yeah, Carlos just mentioned about the first type of design that we wanted to show in this presentation. That was a modified Mother Hubbard, how we can improve the overall gas separation efficiency by adding screens. So now let's go over like the second one, which is a Pata type gas separator. Now this has been in this industry for quite some time now. One of the things that I would like to show y'all is a particular design that helps in improving the traditional Pata type gas separator that we have right now. As Carlos mentioned about the flow path, we'll just go over that again just here in a bit. So if you look on the left-hand side, the main three parts for this gas separator to work efficiently is obviously we're going to need a packer, right? Now, like Carlos mentioned, it could be a rotational packer, mechanical, cup type packer. They all have advantages and disadvantages. So depending on the well conditions, we need to see what works best. But the other section is the joints. Now in this particular design, we have about 3 joints, 24 foot each, so which gets us about 72 feet of total length of gas separator. All of these joints are connected with a dual flow connection, as we can see here on the top section of the left hand side image. Dual flow is something that Carlos mentioned again previously, but the dual flow actually has 2 functions. The number 1 function is when the fluid is going through that gas separator, right, inside of the gas separator, these ribs that you all see, on the dual flow, these 3 ribs kind of helps in the baffling of gas. That is one of the design principles used for majority of the gas separators, as Carlos mentioned before. So these dual flow connections, having 2 of those helps in pretty much breaking out. It helps in breaking out the solution gas that is in the solution, that is in the fluid, right? So that is one function. The other function is it helps in like an overall ease of installation. So having a dual flow connection like that helps us pretty much have the dip tube installed individually in all of these sections. So the overall runtime or installation time is greatly reduced by having this dual flow. So like I mentioned, 2 functions. The other thing about having a 72-foot section or a 72-foot tool is that from the outside, if you see, again, I'm going to show you the flow path here in a bit, but from the outside, this tool has a secondary storage sump that is over here. I'm hoping y'all can see see my mouse moving, right? So this section right here, if you put into numbers, right, this section with the 72-foot tool gives us about 7.27 cubic foot of storage area. Now, the way it works or the way it helps in the overall gas separation efficiency is that suppose the pump has a pump off controller or the reservoir conditions or the pressure is not high enough. This storage sump, having that additional fluid stored and that much amount of fluid stored helps not to run the pump dry, right? So let's put some numbers, like suppose we have a pump running at like 7 strokes per minute, lifting about 100 barrels per day. So the total amount of fluid that can be stored, like I mentioned, in 7.27 cubic foot of storage in this section, right? Convert that 100 barrels per day, we get about 0.35 gallons of fluid per stroke, which pretty much gives us, just in this volume, gives us like an additional 154 strokes for the pump to not run dry, like in conditions like I mentioned before. So that is a big advantage of having a 72-foot tool. And again, obviously, the dual flow inside, the more number of dual flows we have, it helps in the baffling of gas. The other section in this design is a screen section. And that's, again, another advantageous design principle is the coalescence of gas bubbles. So when the fluid exits out at this point, since this is the outlet section, having screens with a really big open area, or the slot size is opened up enough for the smaller gas bubbles that is released inside of this gas separator kind of coalesce and get bigger. So like Carlos mentioned before, the buoyancy effect is higher for these bigger gas bubbles. So it helps in separation of that gas bubbles much easier compared to a slower one. So compared to a slotted outlet section, having a screen outlet section obviously helps in gas separation. Now it has its downsides as well sometimes, especially in wells with a lot of chemical conditions, chemical issues or something. But we need to make sure that we can somehow incorporate a screen, make sure that it's big enough so that it works works as an advantage, improving the separation efficiency. Right. So the flow path, when it comes, we're going to see a video again, but the flow path, if you look on the right hand side, right, we can see the fluid from the formation has to travel inside of whatever we have right below the packer, and the fluid has to go inside of the separator. That's what the packer is supposed to do, is redirect the flow inside of the separator around the dip tube, traveling upwards, and then the gas liberation process, which I'm going to show you in the next slide, helps all happens inside of this gas separator. And the outlet section, where we have majority, if not all, of the gas separation, where we have fluids traveling down, gas traveling upwards, and fluids going into the intake of the dip tube, and goes to the pump. So that's pretty much how the flow path that works. And this is the design and some of the ways that we can improve the design of a traditional packer type gas separator. So let's move on to the video. We'll see now in this particular case with the rotational packer. Now that is something that we do recommend using a rotational packer, which helps in wells with underlying conditions like chemical or sand issues. We're going to talk about it here in the next few slides again as well. But this is pretty much right above the packer. We have our slot intake. Now this slotted intake, that is what connects to the pump, the dip tube. And then we have our dual flow connections in the more number of sections we have. We can play around with the length of the tool based off of the well conditions. So we don't necessarily always need to run a 72-foot. That does help, but we can modify that just because none of this is welded together. So here we have about 3 dual flow connections in all of these systems. Like I mentioned, these 3 ribs helps in baffling of the gas bubbles. So the fluid flow coming from the formation is directed inside of the separator. Now this right here, the way it goes around the dip tube is with our patented intake collar section right here, where we are not straight up going inside of the dip tube and going to the pump. So we have it redirected around the dip tube, goes to the inlet section. Majority of the separation happening in this section right here, where the gas bubbles coalescing because of the screen as well, and then traveling upwards through the annulus, fluid being denser, falling down due to gravity, and goes to the intake section. This intake section, like I mentioned, this is the design because of which we can allow for this system to work the way it's supposed to. And finally, through the dip tube, where we have either compress it or whatever free gas we have still, compress it back into solution and pump it. So that is what we have for the packer type separator. Let's talk about the gas liberation process. So again, like I mentioned, the first section where we have all of the fluids traveling inside of the tailpipe or whatever mud joint we have below the packer, going around the dip tube. Now, like Carlos mentioned, we're using the annulus section, to slow down the liquid, but inside of the separator itself, we have a restricted, or we have a low area where we're increasing the velocity of the fluid, but in turn reducing the pressure. So trying to release as much gas from the solution as possible, be it smaller or bigger, but eventually having the screen outlet section, the number 3, it helps in the coalescence, and gas being lighter and bigger bubbles being much lighter keep travels up the annulus and is separated, where the fluid being denser goes down through the intake. And again, in all of these sections, when it's traveling upwards, in this section, we have our dual flow connection, which helps in the baffling of that gas. So overall, trying to apply the same principle as, this is a packer type, but just improving in whatever way we can to separate as much gas as possible before the fluid reaches the intake section. And the way we do or calculate or put numbers to this is based off of the well conditions. We find out what the in situ gas volumetric rate is. We find out with that fluid production and the length that we have, or that we calculate to be the best, what liquid velocity can be found out in the annular area, and the bubble rise velocity is calculated. Using this, we find out natural separation efficiency, because of which we are getting the amount of total in situ gas or in situ liquid volumetric rate that enters the pump, and also the gas that is ingested by the pump after the separation. So none of the separators are going to be separating 100% of the gas. So just to put numbers to it is something that we make sure that we analyze and calculate way before we recommend this to our clients. So that is this calculation and this calculator I'll be showing you all in the selection criteria as well here in after a few slides. That was the packer type. Now let's come to our third and the final design type. Now this is something that has not been in the market for a long time, but we've been working on this design for a while now, and it's called the chamber type gas separator. Now the way this works is, if you look at on the left hand side, it's pretty much like 2 stacked modified Mother Hubbard style separators, but design, what needs critical design parameters are this middle section right here has to be sealed so that both of these gas modified Mother Hubbard style separators work as individual gas separators. The other design, very critical design parameter for this type of chamber, for this chamber type gas separator to work, is the ID of the dip tube in both of these chambers. Now I'll talk about why we need that. So overall, if you think about it, having 2 individual separators, if we can have a good enough fluid distribution in both of these chambers, we're going to get a much higher separation efficiency in every stroke. So we're going to separate individually in both of these separators, so giving us an average much higher gas separation efficiency compared to a modified Mother Hubbard style. Well, the aim to design this type of separator was to get us a close enough, if not higher, separation efficiency compared to a packer type, but without the use of a packer. Now we know, there are a lot of these deviated wells where no matter what kind of packer you use, you're still going to have some kind of leakage because of the deviation, high dog legs. That is exactly what we're trying to eliminate by using this type of design, where we can install even in deviated wells without any kind of leakage because of no packers. Now let's think about having the same ID in the dip tube on both of these chambers. What is going to happen if that's the case, right? Majority of the fluid is going to tend to go through this top chamber. Why? Because the energy consumed by the fluid is going to be much lower in this for the fluid to travel in this ID or this dip tube compared to this longer dip tube, which is almost twice as much. So the overall pressure drop inside of the dip tube is much higher if the fluid goes through this compared to it goes to the shorter dip tube. And that is exactly why we needed to make sure we calculate what exactly can give, an even close to even distribution in both of these chambers. And after calculations and testing, we found out about having for 2 7/8 tubing to get a 0.75 inch dip tube ID in the top chamber and about 1 inch dip tube ID in the bottom chamber, which gives us, about 55-45% distribution in both of these chambers. So overall, we can have two individual separators working in conjunction with each other and giving us an overall high separation efficiency. When it comes to the flow path, it's going to be similar to what we see in a Mother Hubbard style, right? But the only thing is that we're going to have, if you see very closely, we have these two slotted intakes. So the fluid and gas separating in both of these chambers individually and purging out of the top slots. I'm not sure if you can see it entirely in this image, but we have like two slots right at the top section, the next section of both of these chambers, which helps to purge out those the free gas, whatever enters the system. But majority happens outside because of the IDs and pressure changes. So this is pretty much the principle, the design principle of this separator. Now, we all can see an additional or an optional tool called the gas vent. I'll show this tool here in a bit on why it helps in improving the overall gas separation efficiency. The size is pretty much similar to what we've been having in using in our regular modified Mother Hubbard style separators. All right, so the gas liberation process, again, like I mentioned, both the modified Mother Hubbard style separators working in conjunction with each other and liberating gas individually in both of these chambers. And we're going to have 48 foot of this tool. I'm not sure if I mentioned before, so it's about 24 foot each, just like what Carlos mentioned before in our slotted gas shields style separator. All right, so the calculation is pretty similar to what we do in all of our separators. And what we try to find out is after having these two individual chamber type separators, two individual gas separators, see what percentage of gas we can separate both individually and then averaging out to get like an overall much higher separation efficiency, which I'll show you all here in the selection criteria. And finally, just use the separation efficiency to find out what gas can be ingested by the pump after the separation process. All right, so this is the tool that I was talking about. That was pretty much when it comes to just the designs of all three types of separators, just the modified Mother Hubbard, packer type, and a chamber type separators. If you all have any questions, please feel free to either email us, call us, or you can ask it right now in the comment section below. So this gas vent system, that is an additional, it's just like it's a valve system which opens and closes, and it's compatible in all three types of gas separators that I've just mentioned. It's compatible with the modified, the packer type, and the chamber type, and it's installed right above all of these separators below the seating nipple. Now, the way it works is, I'll show you this video in a bit, but the way it works is just like I mentioned, it's a valve system. So in every downstroke of the rod pump, the valve pretty much opens up because of the pressure exerted by the gas inside of the dip tube. And it creates it opens up a pathway for that gas to liberate or escape out of the dip tube before it goes to the pump in the upstroke. So this is pretty much, no matter what gas separator we use, we're still going to either have some kind of free gas, whatever we try to separate outside of the gas separator, and that goes inside of the dip tube, or hypothetically speaking, we separate like 100% of the gas, we're still going to have some solution gas trying to escape out inside of the dip tube because of the pressure changes, right? So no matter what separator we use, we're still not going to get 100% pump fillage. But so that's exactly why this gas vent system helps in overall increasing the separation efficiency. So this is the flow path we have, similar to a dual flow path, that we have enough area for the gas to escape. So like I mentioned, in every downstroke, we are trying to, so this is the downstroke right here, we're trying to open up or expose this slotted escape section for the gas to escape out. So one of the things that I just wanted to show or for you all to visualize is gas being lighter inside of the dip tube if it escapes out or it's already in a free gas or a free gas section, whatever it is. So it kind of accumulates in the top section of the dip tube. So that is the reason every time this opens up, we can try to purge a percentage of that gas out. So the overall pump fillage can be much higher compared to a system where we do not use this gas vent. So this is the video we'll see. Now this is the section where we have it open and we can see all the gas bubbles or whatever, for as long as it's opened up, we can see the gas bubbles escaping out of this hole. It's pretty small enough for, to make sure we have for the gas to escape out of that system. And as soon as we close that system here, we'll see in a bit, as soon as this is exactly what's going to happen in every upstroke is that it's going to open up and then we're going to have a regular operation. So this is just an additional system that kind of helps in the overall separation of the gas separator. We cannot really, so the calculations that we do is based off of just the gas separator. So this, whatever we get in that number that we get, which we'll see here in a bit, this is just going to pretty much enhance that whole overall gas separation, improving the gas separation efficiency. All right, so that's pretty much what we had for the designs of all three types of separators, how we can improve it. Now let's just look at the calculators of individual separators. This is exactly what I was talking about. We can the way we design is or understand or find out what exactly is the right length, the right IDs and ODs of the separators by finding out the eventual separation efficiency that we can get based off of the well conditions. So just for a modified Mother Hubbard style, like a 48-foot with a slotted intake, we can have about 74% efficiency when it comes to just the separation, considering the volumes and the areas that is occupied by this separator and the casing that we have. So putting all that into consideration, we find out and get about 74% efficiency. Now, one of the pros about having a modified Mother Hubbard style separator is, like Carlos mentioned, we can improve this efficiency by adding a screened inlet section or adding multiple gas bodies to pretty much baffle the gas or agitate the gas for the kind of give a pathway for the solution gas to escape out of the fluid. So that is, like I mentioned, it comes in the pros. Adding an intake section with a screen helps in the overall coalescence, and also in wells where we don't just have gas as the biggest one, we also have severe sand or chemical issues. We can kind of help with screens based off of obviously whatever we are seeing. We need to make sure that we analyze and make this whole system into not only a good modified Mother Hubbard style, but also a two-stage sand filtration system. So that is one of the pros, that we can incorporate this design with it. And also, again, this number can be improved by adding a gas vent right above the separator and just improve the overall efficiency of the system. Now, one of the cons is that we, like, compared to a packer type and a chamber type, the overall separation efficiency is lower. And also, now just for example, we take just a 48-foot modified Mother Hubbard style separator. We see the overall storage sum that I was talking about before with the packer type, which is considerably much lower compared to a packer type. For example, if you're getting about 154 strokes, like I mentioned before, with the packer type, we can expect about 40 to 50 strokes additional with the storage sum inside of the separator. So that is one of the disadvantages, if you want to call that. But like I said, this separator design with just a 48-foot as well can be, or maybe like a 72-foot, having an additional Mother Hubbard can help in low to medium GLR wells. By low to medium, I mean about close to 1500 GLRs or below. Sand can be handled based off of the combination tool that Carlos showed before, having a screen and a desander. But just because we can incorporate that into the system, sand is not really an issue. Scale paraffins, none of the open areas for the system is tight enough for plugging up any section, so we should not have any issues. But we need to make sure that if it is severe, have either a chemical screen, OSI chemical screen right below it, or have some surface chemical treatment above it, or both if it's severe. So these are some of the selection criteria that we have for a modified Mother-Hubbard style separator. Now, for a packer type, one of the things that I mentioned earlier as well is that we recommend to use mechanical or rotational packers, kind of like the best bet that we have in worst case scenarios with sand. But again, this design as well can be incorporated with a desander right below the packer. And if we use that, then yes, then this it's not going to be that big of an issue. But just considering the GLRs and considering the gas separation efficiencies, we can get much higher separation efficiency as calculated with the same pump speed and production rates. So we can get about 84%. Again, this can be improved by adding a gas vent. And also this separation or this calculation does not take into consideration having that coalescence, but it definitely adds on to this overall separation efficiency. So one of the pros, and very important pros, like I mentioned before, is having a total volume of secondary sump that is in this annular section outside of the separator, where we can store gas-free liquid. And the system does have an isolation system which can actually act as a pro and a con. The way, if at all, suppose we do have quite a lot of issues when it comes to sand or chemicals, and we don't take that into consideration and add no desander or no chemical treatment, or the right chemical treatment, that can actually be can hurt the system since having an inlet right next to the packer, the sand getting accumulated in the system or above the packer can actually restrict the flow eventually. So that is something we need to make sure that we keep in mind and analyze way before we finalize the eventual design. It's not only take into consideration just the gas or GLRs, but also the sand and chemical issues in it. But suppose we do like this. Suppose we just take into consideration the GLRs, we can get above this packer type separator based on what the well has. We can go above 1500 as well. So from low to a high GLR wells, this gas separator can work pretty efficiently. Just taking into consideration just the GLRs of the well. But like I mentioned, the packers, if a cup type packer is used, that can easily make the gas just kind of leak out of the system and go right to the intake of the separator. So the overall, it's not going to kill the overall system, but it definitely will affect the overall separation of the gas separator. So that is something that why we always try to recommend, and this is something we've gotten by experiences. We've gotten much better results now, the separation efficiency by using a rotational packer compared to a cup type packer. All right, with this chamber type now, just the calculation, kind of considering all the parameters that we do consider in our calculator, we do get actually much higher separation even compared to a packer type. So just for GLRs, and now obviously the reason what we do is we calculate the separation efficiencies individually in both of these chambers and then average out to get an overall efficiency. And this makes sense. Like how I mentioned before, if we successfully distribute the fluid equally or at least close to equal in both of these chambers, every stroke we're getting almost twice the separation. So that is exactly why this number makes sense, is because of incorporating two individual separators working in conjunction with each other. Again, like all gas separators, this as well has its downsides. And that is that right now with this design, we cannot incorporate either a screen or a desander, but obviously that's going to be like in our next set of designs or design improvements in this chamber type gas separator. But as of now, just considering a 48-foot chamber type gas separator, having wells with high sand issues, we can, since this section is isolated, we can definitely store some sand, restricting the intake of the upper chamber type. Obviously, if we use some tailpipes below the bottom section, then we can have much storage area. But the overall separation efficiency can be hindered because of underlying issues of the wells. That is not just gas. But if we just look into gas and GLRs, this this well or this type of separator can handle gas or GLRs pretty similar to what we have with the Packer style separator. It's just that the main advantage is that we don't really have to use Packer, like I mentioned before. So in deviated wells and in horizontal wells that we have over here in the Permian Basin, even outside, this type of separator can be very useful in very gassy wells. So the other issue again is not, I wouldn't call it exactly issue, but the limitation is having lower a total volume storage. This is going to be maybe a little lower as well, even compared to a modified Mother Hubbard style. So the separation being excellent, we can have lower storage sum. So we have like a pump off controller in the pump, and we maybe have lower reservoir pressure. But this might be, we might have to look into, either using a Packer type separator or see how we can incorporate this kind of design in such wells. So that is pretty much what I have when it comes to this selection criteria. Just to sum everything up, we have a separation efficiency can go much higher, in the chamber type separator if the way what we've tried to do, and that has been working pretty well. So just considering the GLRs from low to high, the chamber type can be excellent and can work very well in all of those type of wells. Now, Mother Hubbard style wells can work really well in low to medium by adding gas bodies and desanders and screens. Packer type again can be used in really low to high, the whole spectrum of that GLR numbers that we have seen. So again, with issues there in the well with sand or chemicals, we can incorporate a desander or some chemical screens. So that, when it comes to just the separators and the selection criteria, that is what I have, or what we have for you guys. But having, designing the best separator that we have, and just we cannot expect it to work like the way it's supposed to, if at all the operational guidelines or the total BHA apart from the separator is not taken into consideration. By that, what I mean is pretty much most of y'all might have heard about using a TAC. Most of the wells which use a TAC, especially, we always recommend to either use it below the separator or use it about 3 to 4 joints above the pump. The reason for that is if we have the TAC right close, and this y'all must have heard of it already, but just to emphasize on that more, is if we have it right at or below the seating nipple, it kind of creates gas pockets right at the intake of the separator, which can affect the overall separation efficiency. So that is one thing that needs to be considered no matter what kind of separator we use. The other one is the spacing of the pump and the distance between the seating nipple and the gas separator, right? So there are a lot of operators that we've seen that they use a 4-foot or an 8-foot, just a sub right below the seating nipple, and then use a separator. Or the spacing of the pump, if not taken into consideration or evaluated before using a separator, what can happen is we need to see, just for example, we take a 2 7/8, right? We use an 1.25 dip tube. So since 1.25 dip tube is what communicates the fluid from the outside to the pump, if that distance, if that dead space is not managed properly, we can actually kind of affect the overall separation. The separation outside might be great, but inside, just because of having that dead space, it can free out more of the solution gas right before it goes to the pump. So those two are very critical to evaluate right before or when we are designing the BHA. So not just taking into consideration or not just assuming that having a gas separator, no matter what, even the chamber type with high separation efficiency, if we don't take into consideration these parameters or these operational guidelines, it's going to work against, and eventually we're going to see lower pump fillage and high gas interference inside of the pump just because of the spacing between the separator and the pump intake, right? The other one is the type, or is the type of pump. We don't see this much quite often, but just to let you know, traveling barrel and tubing pump, pretty much because of the same reason, having that dead space inside or having much higher space going from 1.25 dip tube to that higher volume is going to be an hindrance to the total separation efficiency or total pumping efficiency, for to be more accurate. All right, pumping speed. Carlos mentioned before. In most of the cases where we have such high gas interference, we do recommend to go the maximum stroke length that we have, and decrease the overall speed of the pump. But now, suppose we've seen a lot of wells where suppose the BHAs could not be modified, or we do have like TSEs, or we do have pump joints right below the seating nipple above the gas separator. In those situations, sometimes it helps in actually speeding up the pump. Why? Because we're not giving that gas enough time to free out. So we need to kind of play around with that pumping speed based off of the BHA. So, but if everything is the way we recommend, and we have a gas separator just the way it's supposed, or a gas separator for a particular well, we have the BHAs all designed the way it's supposed to be, we do recommend a lower pumping speed, something you'll probably already know about, but that's very critical in overall pumping efficiency to be higher. Casing pressure needs to be kept a minimum, and tubing pressure needs to be kept a little higher, especially in severe gassy wells. But we need to make sure that we don't affect the production, right? That's pretty much what we're all after. We cannot add enough back pressure inside of tubing and affect the overall production. So we need to play around with those parameters and see that what gives us the best results even after using a gas separator. But yes, that's pretty much what we have for you guys today. We have discussed about all the different types of separators. Carlos did a great job about talking about the way we can improve the modified Mother Hubbard style separators. We spoke about the new chamber type gas separator, and also some of the design changes in the traditional packer type, how to improve the overall separation efficiency. This is what we have. We're going to stay here for a bit. If at all there are a few more questions that you'll have, we can answer those. But if y'all don't have right now, and if there's absolutely anything that comes up later on, we have our contact information here. Feel free to call us or email us with whatever questions y'all have. But thank you all again for joining us. And
thank you, Neil. All right, so we're gonna continue with the question Q&A section. So we have one question here on Zoom. Then we're gonna go through the ones that the people send through YouTube. So the question is, can you quantify how much gas into the pump can be reduced by the gas vent tool? So basically, I mean, yes, we can. So what we can do is just calculate how much gas is ingested by the pump, and then just run like a nodal analysis, like pressure and separation efficiency. So let's imagine that. So we're ingesting, I don't know, of free 60 MCF, and then we will have a separation efficiency. So then what we can do is, but in this case we will need the PVT properties, so to know the deep tube. All right, and then so what we can do is analyze that pressure in that point in the gas vent. So what I'm trying to say, like, it is possible. We just will need to have the basically PVT properties information, so we can calculate the properties on that specific point, so to see like how much gas the vent tool is capable of separating. Also, I will need to evaluate of the pumping speed and the pump the stroke length. So we can just basically calculate that, but yeah, it's absolutely possible.
Right. One of the things that I did mention when it comes to selection criteria, and we have a question on the GLR limitations of just a modified Mother Hubbard style is that we can improve that separation efficiency. Like I mentioned, it does not have to be just below 1500 GLRs too. We can extend that a little bit more. The way we can do it just by adding those two special components like the screen, which helps in the overall separation efficiency, adding multiple gas bodies, which not only will increase the storage sum inside of the tool, but also from the outside play around or agitate the gas enough to separate as much as we can, and obviously the gas vent that we just mentioned. So we're not limited, but what we can do is, what we have been doing is that we've been designing a little longer tools. Um, and making sure that whatever GLRs that we have in that particular well and what efficiency that we are getting. So it is not, like I said, it's not limited to just below 1500 GLRs or no. But yeah, obviously the other two types of separators kind of work much better when it comes to just the GLRs.
All right. Neil, you got more questions over there?
Yeah, the other thing about the packer type that they're mentioning is the question is, and which is it's a very good question, that since we have that storage sum, that much amount of storage sum, we're going to have a bunch of stagnant fluid in that section. So the question is, can we see, like in corrosive wells, can we see a lot of issues with hole in the separator? And that is possible. That is definitely possible if the right chemical recommendation is not done, because like I mentioned, that storage sump helps in not running the pump dry. But again, if it's one of those severe wells, we're gonna have to make sure either have a chemical screen even below, so to treat the fluid before it enters the pump and stores, enters the separator and stores in that annulus. And also if we can have some kind of surface treatment. So both treatments, if chemically, if we take care of it, and we need to, especially in that packer type.
Perfect. All right. So there, one second. So there. So do you have any case studies on the Packer type gas separator? So yes, we do. Actually, we do have two papers. One for the SPE, and the other one for the Southwestern. So we can share those absolutely. We will be leaving those the papers, or I can send the papers themselves. So just please leave your email, all right, and we or contact us to either Neil or me. Send to your, like we have two successful case studies when we increase the production efficiency with the installation of a Parker type gas separator.
We have, like I mentioned, our chamber type is a comparatively newer design and comparatively newer type of gas separator. We've not had a bunch of wells that we've installed it in, but we are trying to make sure that we do it, and so we can get much more results. But right now, we've had a few installations where we made sure that the underlying conditions of the well is not sand, or at least the chemicals are taken care of. So we're seeing we're seeing much higher pump fillage, at least initially, but it's too early for that, to actually get a case study out of it. And but we're working on it, and we are, excited to show, the results that we're getting out of the chamber type separator, being a comparatively newer style of separator.
Right, that's right. All right. Okay. All right. So we have. So it says. So why don't you use a packer type, or what would be the advantage of using different kind of packers with the packer type gas separator? So basically, I mean, what we want to do is, as Neil explained before, as Neil explained before, there is the necessity of isolation of the zone, like 100% isolation. So we have a GV compactor, and then some of the gas just leak to the packer, and it will flow inside of the deep tube and just right to the pump. So basically, a mechanical packer and a rotational packer, they're gonna provide a better seal. However, there in some cases the mechanical packer will have some problems releasing that packer of that because of the sand that most likely will be deposited on top of it. So that's something that we need to consider. So we always advise to go with this more like reliable seals, because what happens is that sometimes, I mean, and we do this, like the sand helps to seal the GV packer, and it can provide like a big, very good seal. But in terms of gas, so it's better to use like these kind of packers, because it will give you more reliability, and so it will provide like a higher efficiency on the separator. You will feel like more comfortable with this kind of packers.
And we've actually even seen, just based on what we have heard back from the clients, is just right after installing a packer type with a cup type packer, and then not getting, or having that leak because of the packer, and then changing it out to a rotational packer, just the overall improvement of the pump efficiency it's visible, and we've seen that. And that's the reason why it's not just based on our calculations or understanding. It's based on what we, on the feedback that we get from the clients that we work with. So, but yeah, that
Yeah,
is an excellent point.
absolutely. And another point that maybe we need to consider, that there are many clients, many operators, they prefer not to run any packer at all, because they have had like bad experiences pulling. They have run like longer days try to pull that packer because they got stuck for some reason, right? So that's when the chamber type separator could be a very good opportunity to approach that problem, and gather really good data we can use later on to keep developing more and more efficient gas separators.
And yeah, I mean, that was pretty much the motivation behind designing such a tool. But since there are some similar chamber type separators in the market, you all can take a look at one of the limitations that it can have. That is basically having that the opening of the dip tube in multiple chambers. We need to make sure that that's kind of calculated and divided the way it's supposed to, so that the total pressure drop needs to be taken into consideration if we need a chamber type to work as a chamber type separator.
Correct. Perfect. I don't have more questions. Do you have more questions?
Don't see any, but these are our numbers and emails, so feel free to call us, email us with whatever questions you all have. If you all want us to share whatever data you all want us to share with you guys, we'll do that.